Hello dear students. Today we are going to discuss about an important concept called couple. Before speaking about couple, we should know or we should have a clear picture about the equilibrium of rigid bodies. Then only we can able to understand what couple is. So first we shall speak about equilibrium of rigid bodies. Here, any body can possess two kinds of motion. One is translational and another one rotational motion. Translational and another one rotational motion. If any body has to be in a state of mechanical equilibrium, any body must be in a state of mechanical equilibrium, then it should satisfy two important conditions. One, it should possess a translational equilibrium, and other thing, it should possess a rotational equilibrium. So, if a body is said to be in a state of mechanical equilibrium, then the body should be in a state of translational equilibrium as well as rotational equilibrium. Now, we shall speak about the conditions which will come under the category of translational equilibrium, and we can speak about what translational equilibrium is. If forces are said to be acting on a body, a rigid body, then if the object is said to be at rest or otherwise it is said to be moving with a constant velocity, then we can say the body is said to be in a translational equilibrium. In other words, I can say the sum of the forces acting on the body must balance each other, or the net force acting on the body must be equal to 0. If this condition is satisfied, then we can say the body is said to be in a state of translational equilibrium. So, we can say in translational equilibrium, what is the condition existing? If so many number of forces are said to be acting on a rigid body, if the body is said to be at a state of rest or moves with a constant velocity, if it is said to be under rest or it is moving with a constant velocity, then what does this mean? The net force acting on it is said to be 0. If the net force acting on it is said to be 0, then we can put it in other words, F net is equal to sum over I equals 1 to n, F of I vector, this is equal to 0, which means n number of forces are acting on the body, rigid body. Each and every force acting on the body must balance each other. So the forces acting on the body must balance each other, so that the effective or the net force acting on the body must be equal to 0. Then this can be explained in this way: sum over f of x equals f vector equals sum over f of y vector equals sum over f of z vector is equal to 0. What does this mean? The forces acting along the x direction are tending to balance each other. The forces acting along the y direction tends to balance each other. The forces acting along the z direction tends to balance each other. Hence, net force acting on a rigid body is balancing each other. So, or if so many number of forces are acting on the body, one force is balancing the other, hence the net force acting on the body is equal to 0. Or the vector sum of all the forces acting on the body must be equal to 0. We can put it this way: the vector sum of the forces, all the forces acting on the body must be equal to 0. So this is the condition to bring out translational equilibrium. So by Newton's second law, I can write F vector is equal to ma vector, which is equal to 0. This F vector is F external. If external force is 0, then the product of mass into acceleration is 0. Then we can say acceleration is 0, because mass cannot be 0, because if force is acting on a body, it will possess a mass. Mass will not be 0. So acceleration possessed by the body will be equal to 0. So linear acceleration will be 0. If acceleration is taken into account, then you have to speak about velocity. A equals dv divided by dt. If acceleration is 0, rate of change of velocity is also 0. So we can say the velocity will be either equal to 0 or constant. Why? Differential of a constant is 0 or differential of 0 is 0. So either the velocity of the body will be equal to 0 or constant. In the beginning we saw if a body is said to be in a state of translational equilibrium, then the body must be at rest, at a state of rest, or must move with a constant velocity when forces act on the body. Here we are bringing out that condition. The velocity is becoming 0. If velocity is 0, body is not moving, body is said to be at rest. If the velocity is constant, the body is said to be moving with a uniform velocity or with a constant velocity. So, what are the conditions we are listing out here? If we are speaking about translational equilibrium, these conditions must come into play. Along with this, we have to speak about linear momentum. When you speak about linear momentum, we can write P vector is equal to mv vector. As velocity is constant, linear momentum is also a constant. Linear momentum of the body, rigid body, is also a constant. And other idea is that linear momentum is constant. If you speak about this translational equilibrium, here we can speak about two kinds of equilibrium. This translational equilibrium can be listed out into two: static and dynamic equilibrium. Static and dynamic equilibrium. Why? Reason is very simple. We are speaking about the velocity of the body to be either at rest or moving with a constant uniform velocity. If the net forces acting on the body make the body to stay at rest, then we can say the body is said to be in a state of static equilibrium. If a body is said to be static, that is different. Body is said to be in a state of static equilibrium, then all the forces acting on the body is balancing one over the other, resulting in the state of rest. We can say it makes all the forces acting on the body makes the body to remain in the state of rest. So a static equilibrium is said to be attained. If a static equilibrium is discussed, velocity is 0, linear momentum P is also 0 in this particular case. For static equilibrium, velocity is 0, linear momentum is also 0. For dynamic equilibrium, velocity and hence linear momentum are constants. Velocity and hence linear momentum are constants. So, if you are speaking about translational equilibrium, the conditions are the body, net forces acting on the body must make the body to stay in a state of rest or should make the body to move with a constant velocity. In other words, I can say the net force acting on the body must be equal to 0, or sum of all the forces acting on the body must be equal to 0. Sum of all the forces acting on the body, vector sum of all the forces acting on the body must be equal to 0, which means all the forces acting on the body are said to be balancing between each other. So, net force must be equal to 0. So, conditions are net force acting on the body must be 0. Then, acceleration of the body based on Newton's second law, linear acceleration of the body must be equal to 0. Third condition, the velocity of the body may either be 0 or constant. If velocity of the body is 0 or constant, then the linear momentum of the body may either be 0 or constant. In general, we say linear momentum is constant. When you speak about static equilibrium, there the velocity is 0, linear momentum is 0. When you speak about dynamic equilibrium, velocity and hence linear momentum are constants. So when you speak about translational equilibrium, all these ideas should come into your mind. Then we shall go for rotational equilibrium. What is the condition which explains about rotational equilibrium? A body is said to be in a state of rotational equilibrium when the body does not rotate or the body rotates with a constant angular velocity. Body rotates with a constant angular velocity. In other words, we can say the net torque acting on the body is said to be 0, or the vector sum of the torques acting on the rigid body is said to be 0. In other words, I can say the sum of or algebraic sum of, you can say put it in the form of vector. but even with magnitudes also we can calculate. So the algebraic sum of the moments of all the forces acting on the body must be equal to 0, which results you with 0 rotational motion, or which results you the body at a state of rest. Body does not rotate. So what is a state of rotational equilibrium? You can say for rotational equilibrium the body does not rotate, or it rotates with a constant angular velocity, which means the net torque acting on the body must be equal to 0, or the vector sum of the torques acting on the body must be equal to 0, or the sum of the moments of all the forces. What is moment of force here? It is simple. It is the product of force into perpendicular distance from the point of rotation. So moment of force, moment of all the forces, sum of the moments of all the forces acting on the rigid body must be equal to 0. So the torque acting on the body must be equal to 0. This is the key idea which is required to speak about the rotational equilibrium. We shall see that also. For rotational equilibrium, the net torque must be equal to 0, which is also equal to sum of I equals 1 to n tau I vector. This is equal to 0. This is equal to 0. Mathematically we can express, as the equation of motion, we can express sum over I equals 1 into 1 to n tau I vector is equal to 0. Sum over I equals 1 to n tau I vector is equal to dl vector divided by dt, which is equal to 0. What is this L vector? Angular momentum. Angular momentum. So L vector is equal to 0. So when you speak about rotational equilibrium, the angular momentum of the body, rigid body, will be equal to 0 when you speak about rotational equilibrium. L vector is equal to 0. When you consider a body which is a light thin rod which is pivoted at some point, let us say C, ends of the rod is said to be AB, two forces are said to be acting, F1 and F2, let us say F1 and F2, two forces are said to be acting. The distance of the center from one end is said to be D1, the distance of the center from the other end is said to be D2. Then when you calculate the moments, because while speaking about rotational equilibrium we are discussing about the moments of forces also. So we shall see how the expression exists. The moments of force, the net moment of force, or the sum of the moments of all the forces acting on the body must be equal to 0. So I can write the condition F1 D1 minus of F2 D2 must be equal to 0. F1 is said to be acting on A in the downward direction. F2 is also acting on the body at the end B in the downward direction. Two forces are parallel to each other. They are acting in the downward direction. This F1 will produce an anti-clockwise moment. F1 will produce an anti-clockwise moment. F2 will produce a clockwise moment. F2 will produce a clockwise moment. As a matter of sign convention, anti-clockwise moments are taken positive. Clockwise moments are taken negative. So if net torque or net moment of force must be equal to 0, net torque must be equal to 0. Both are one and the same. So this condition will arise. F1 D1 minus F2 D2 is equal to 0. Why? F1 D1 is the moment produced by the force F1. So I can take it as torque tau 1. F2 D2 is the moment produced by the force F2. I can take it as the torque tau 2. But torque is a vector quantity. Anti-clockwise moment must be given a positive sign. So tau 1 is taken positive. Clockwise moment must be given a negative sign. So tau 2 must be taken negative. So tau 1 minus of minus plus tau 2 is equal to 0. So statement is very clear. The net torque acting on the body is equal to 0, or the sum of the moments of all the forces acting on the body is equal to 0. So condition exists here. So the net torque acting on the body must be equal to 0, or otherwise the sum of the torques acting on the rigid body must be equal to 0, or the total angular momentum of the rigid body must be equal to 0, or the sum of the moments of all the forces acting on the body must be equal to 0. If these conditions exist, then the body is said to be in a state of rotational equilibrium. If the net torque is 0, body is said to be in rotational equilibrium. If the torque is not 0, body is not in rotational equilibrium. That is the key idea. Now, if tau vector is equal to 0, you can bring out another condition here. If tau vector is equal to 0, tau vector equals I alpha vector, relation connecting torque and angular acceleration. If tau vector net torque is 0, then this condition is also equal to 0. Moment of inertia cannot be 0. So obviously alpha, which is the angular acceleration, that must be equal to 0. So if a body is said to be in a state of rotational equilibrium, then angular acceleration of the body must be equal to 0. So angular acceleration will become 0. Angular momentum of the body will become 0. The net torque acting on the body will be equal to 0. Or the sum of the moments of all the forces acting on the body will be equal to 0. Or the sum of the torques produced by different forces on the body will be equal to 0. If all these conditions are discussed, or if all these conditions do exist, then we can say the body is said to be in a state of rotational equilibrium. So, if you speak about equilibrium, states of equilibrium, if a body is said to be in mechanical equilibrium, then the body should possess translational and rotational equilibrium. We cannot expect this condition to exist in all the cases. Why? There are cases where you can get partial equilibriums also. Partial equilibriums. Partial equilibrium in the sense, body will have a translational equilibrium, but it won't possess a rotational equilibrium. Or if a body is said to be in a state of rotational equilibrium, then it won't possess a translational equilibrium. If this kind of conditions exist, then we can say the body is said to be in a state of partial equilibrium. If partial equilibrium exists, then we can speak about what couple is. We shall continue. Before going to that, we shall list out, or we shall compare between this, make a comparison between translational and rotational equilibriums. As we discussed, there are certain conditions where partial equilibrium also will exist, where if a body is said to possess a translational equilibrium, then rotational equilibrium will not be existing. If the body is said to possess a rotational equilibrium, if the body is said to possess a rotational equilibrium, then the translational equilibrium will not exist in the body. If such conditions exist, then we can say the body is said to be in a state of partial equilibrium. Let us consider a light uniform rod of certain length. The ends are A and B. Let us say C be the midpoint of the rod. Two forces are acting on the rod at the ends in the parallel direction, F1 and F2. Two forces are acting on the rod. Let us say C is the midpoint. Let us say the distance of the midpoint from one end is D1. The distance of the midpoint from the other end is taken to be D2. Then, if you look at this particular case, the two forces are acting along the same direction. Two forces are acting along the same direction, in the downward direction. Then, when you calculate net force here, F net is equal to F. I can mark these forces as F and F. Two equal forces are acting. So F net is equal to F plus F. This is equal to 2F, which is not equal to 0. If the net force acting on the body is not equal to 0, then the state of translational equilibrium does not exist. So the body is not in a state of translational equilibrium. What about the rotational equilibrium here? You can calculate. Force will produce an anti-clockwise moment here, and this force F acting at the end B will produce a clockwise moment here. So two moments are acting, but they are acting in the opposite sense. So when you calculate the net torque, we can say tau 1 vector plus tau 2 vector will be equal to 0. This we saw earlier. So due to this action of forces F and F on the ends of the rod AB, there is a net torque which can be calculated as tau 1 vector plus tau 2 vector, which will be equal to 0, because the moment produced by one force will be equal and opposite to that of the moment produced by the other force. This tends to make the rod to rotate in the anti-clockwise direction about the point C, whereas this force acting on the end B will make the rod to rotate in the clockwise direction, or will produce a clockwise moment about the point C. These two moments will be having equal magnitude, but they are acting in opposite directions, so the net torque will be equal to 0. If net torque is 0, then the body is said to be in a state of rotational equilibrium, but net force is not equal to 0, so the body is said to be not in translational equilibrium. Body is said to be not in translational equilibrium, or it does not possess translational equilibrium. So a partial equilibrium state exists in this case. You can go with another example. The same rod. The only difference what you have done on the rod is this. C is the midpoint. Distance from A is D1. Distance from B is D2. The same force F is acting in the downward direction or the end A, but the same force F is acting opposite to the force acting at the end A. So two equal and opposite forces are acting at the ends of the light rod AB. So when you calculate net force, F net will be equal to 0. How? We can say F vector. One force is acting in the downward direction. If I consider the downward direction as positive, then the upward direction must be taken negative. Or if F is taken negative, downward direction is taken negative, then the upward direction must be taken positive. So one force is in downward direction, another force is in upward direction. So one will be positive and another one will be negative. So net force will be equal to 0. One force is balancing the other. This is the condition. Body is said to be in a state of translational equilibrium. The rigid body is said to be in a state of translational equilibrium. What about rotational equilibrium, tau net? You can say, if you calculate torque, this produces anti-clockwise moment. Anti-clockwise moment is taken positive. So generally, while speaking about net moments produced or sum of the moments produced, I have to write tau net is equal to tau 1, or when you write in terms of magnitude, tau net equals tau 1 minus of tau 2 must be equal to 0. So this is the condition. But here, if you calculate the net torque, you can see an anti-clockwise moment is produced by the force acting at the end A about the point C. And this F will also produce an anti-clockwise moment about the point C. So the two forces are producing anti-clockwise moment. So the rod will be set into rotation about the point C. So net torque is not 0. So net torque is not 0. If net torque is not 0, then the body is not in a state of rotational equilibrium. Not in a state of rotational equilibrium. So what happens here? Two equal and opposite forces are acting on a body, and they are separated by some perpendicular distance. Their line of action are different. The forces whose lines of actions are different, and these two forces sets the rod to undergo rotation about the point C. So we can call these two forces as a couple, which is said to be acting on the rigid body. So a partial equilibrium state brings out the idea of couple. If couple has to exist, there should be a state of translational equilibrium, but the body should not possess a state of rotational equilibrium. In the sense, the body should not be in the state of rest. It has to rotate. So we can say the net force acting on the body must be equal to 0, whereas the net torque should not be equal to 0. If this condition exists, or in other words, if translational equilibrium exists and rotational equilibrium does not exist when forces act on a rigid body, then the body is said to experience a couple. That's the key idea. We can define what is a couple. A pair of forces which are equal in magnitude but acting in opposite directions and are separated by some perpendicular distance. See this one? A pair of forces equal in magnitude, F and F, acting in opposite directions and are separated by a perpendicular distance so that their line of actions or lines of action are different. That causes a rotation. Or that causes a rotation about the point C is said to constitute a couple or is said to be a couple. In short, we can say two equal and opposite forces whose lines of actions are different acting on a body sets the body in rotation is said to be a couple. So a couple is simple. Couple here refers to two. So how the forces must act? The two forces must be equal in magnitude and they have to act in opposite directions. And the two forces should not have the same line of action. They should possess different line of action. So the two forces must be separated by some perpendicular distance. See, the two forces are separated by a perpendicular distance. Their line of actions are different. If this condition exists, then the body will be set into rotation. And the two forces which makes the body to undergo rotation is said to constitute a couple. So, how will you define couple? A pair of forces which are equal in magnitude but acting in opposite directions and are separated by a perpendicular distance whose lines of actions are different so that it causes a rotation in the rigid body, then the body is said to constitute a couple. In our day-to-day experiences, we will be coming across couple in so many activities. Simply, we can say if you are asked to open the cap of a bottle, water bottle, what will you do? You will be applying two equal and opposite forces so that the cap will be opened. In the same way, if a driver drives a car, then what he is doing? He is applying two equal and opposite forces on the steering so that he can able to turn the vehicle. In the same way, you can just go on with so many number of examples. Couple always do exist. Right? This is a kind of a simple lever. This is going to be discussed in the next heading. The same idea, what we had. If two equal and opposite forces are acting on a body, from which we are bringing out the idea of couple. In the same way, we saw another example. Two forces are acting parallel and in the downward direction. Then, what will happen? You saw a condition over here. We shall apply this idea to speak about the principle of moments. So, you can just kindly recall what are the places or where are the places you are coming across this idea couple. You can give out so many number of examples. Even if you use a Camlin pen, then when you want to remove the cap of a pen, what will you do? You will be applying the couple over the cap so that it will be removed. In order to open a tap to take water, what will you do? You will be applying two equal and opposite forces. Without knowing what you are exactly doing, you will be applying couple in your day-to-day activities. Daily, every day, you are applying this couple. So, what is couple? A pair of forces which are equal in magnitude but are acting in opposite direction and are separated by a perpendicular distance whose lines of actions do not coincide so that it causes a rotation in a body. If this happens, then this the pair of forces is said to constitute a couple. We shall now speak about the principle of moments. According to principle of moments, a body will be in a state of rotational equilibrium when the sum of the moments of all the forces, we can say, for example, F1 d1 minus of F2 d2 will be equal to 0. The sum of moments of all the forces acting about a point must be equal to 0. Sum of moments of all the forces acting on the body about a fixed point must be equal to 0. This is principle of moments. As a matter of sign convention, we can say anti-clockwise moments are taken positive and the clockwise moments are taken negative. So we can put this principle of moments in other words that the sum of clockwise moments is equal to sum of the anti-clockwise moments. So what will happen? If you take the algebraic sum of all the moments, then the net moment will be equal to 0. net moment of force will be equal to 0. That's the idea. So sum of clockwise moment is equal to sum of anti-clockwise moments. So what principle of moments is saying, if a body will be in a state of rotational equilibrium when the sum of moments of all the forces acting on the body about a fixed point must be equal to 0. If you apply sign convention for clockwise and anti-clockwise moments, then we can put this statement in a different way, that the sum of clockwise moments is equal to the sum of anti-clockwise moments. Let us consider a thin light rod of certain length, whose ends are AB. Let us say at a point O, the body is said to be pivoted. We used to call pivoted. Pivoted here refers to fixed. Pivoted means some object which is placed over sharp point is said to be pivoted. So this is a kind of knife-edge sort of thing which is supporting the rod here. So we used to call this as fulcrum. So at the point O, it is pivoted. At the ends A and B, two forces are acting. I can say the forces are either I can take it as equal forces or different forces. I can take it as F1 and F2. So F1 is the force acting at the end A, which is at a distance D1 from the pivoted point O, and another force, let us say F2, which is acting at the end B, which is at a distance D2 from the same pivoted point O, right? And we can say this pivoted point, which we used to call, or the fulcrum, is exerting a reactive force at the point O, or which is acting in the upward direction. A normal force or reactive force is acting on the rod in the upward direction. So a reactive force is acting in the upward direction, and the two forces F1 and F2 at the two ends A and B are acting in the downward direction. Now the lever is said to be, you used to call this as a lever. This rod, what we have assumed or taken, is termed a lever. This one is lever, not liver, lever. This is termed a lever. So what are the examples of a lever? We can say a seesaw in children's ground, and we can go with so many number of examples. Whatever you use, a iron bar which is used to lift up a huge stone with the help of a fulcrum, that is also an example of a lever. We can go with so many number of examples. Balance, or in a physical balance or in a beam balance, the horizontal rod which is provided is also a lever. So a lever is considered here. Here the pivoted point, at the pivoted point the reactive force is acting in the upward direction, and I am assuming giving the name fulcrum for this pivoted point, and this one, the support which is acting on the lever, is termed fulcrum. Two forces F1 and F2 are acting in the downward direction, and the reactive force is acting in the upward direction. Now, the lever is said to be in a state of mechanical equilibrium. Listen here. The lever is said to be in a state of mechanical equilibrium. If the lever is in a state of mechanical equilibrium, then you can say, first one, it should possess a state of translational equilibrium. Translational equilibrium. It should possess a state of translational equilibrium. What is the condition required for translational equilibrium? Net force must be equal to 0. What are the net forces here? If I am assuming the upward force as positive, then the downward forces can be taken negative. How many forces are acting here? Three forces: F1, F2, and R. F1 is acting in the downward direction, F2 is acting in the downward direction, or reactive force is acting in the upward direction. So net force acting on the lever is 0, which means if the lever has to be in a state of translational equilibrium, then I can write R minus F is equal to 0. Why I am writing minus F? These two forces are acting in the downward direction. So from this I can write R equals F1 plus F2, which means the net force F1, F2 acting in the downward direction, or the forces F1, F2 acting at the ends in the downward direction is equal to the reactive force acting in the upward direction at the point of fulcrum. So R equals F1 plus F2. This is one condition. Then the same lever should also be in a state of rotational equilibrium. So if the lever is said to be in a state of mechanical equilibrium, then these two equilibrium states must be maintained. Then translational equilibrium is that the body or the lever should also possess rotational equilibrium. For rotational equilibrium, we can write the condition. F1 is the force. D1 is the distance of the force F1 from the fulcrum. So F1 D1 minus of F2 D2 is equal to 0. Minus of F2 D2 is equal to 0. So the moment produced by the force F1 minus of moment produced by the force F2 must be equal to 0. How this condition is coming? I told you already that the sum of the clockwise, I told you already that the net torque acting on the body must be equal to 0, or the sum of the torques acting on the body must be equal to 0, or the sum of the moments of forces acting on the body must be equal to 0, as there are two moments existing. See this one, this force F1 will produce anti-clockwise moment, and the force F2 will produce a clockwise moment. So anti-clockwise moment is taken positive as a matter of sign convention, and the clockwise moment is taken negative. So if you write the condition as F1 D1 minus F2 D2 is equal to 0, then only you can achieve the condition for the net moment, or the sum of the moments produced by the various forces acting on the body must be equal to 0. So we can write here F1 D1 minus of F2 D2 is equal to 0. Once again I would like to recall, the F1 D1 is the anti-clockwise moment. This is positive, torque is positive. F2 D2 is clockwise moment. This must be taken negative, minus tau 2. Minus of minus will become plus, so tau 1 plus tau 2 will be equal to 0. Net torque is becoming 0 here. So we can say the body is said to be in a state of rotational equilibrium. Now from this equation, let us say this is 1, this is 2. From equation 2, from 2, we can write F1 D1 is equal to F2 D2. And I can write F1 by F2 is equal to D2 divided by D1. This ratio F1 by F2 is called mechanical advantage. MA is mechanical advantage. What is mechanical advantage? Mechanical advantage is the measure of the force amplification achieved with the help of a machine tool. Achieved with the help of a machine tool. Mechanical advantage is the measure of force amplification achieved with the machine tool. So mechanical advantage is the measure of a force amplification achieved with the help of a machine tool. We can understand that with this expression. Mechanical advantage is equal to F1 by F2 is equal to D2 divided by D1. And we can say here from this expression F1 D1 is equal to F2 D2, we are once again getting the statement for principle of moments. F1 D1 is the anti-clockwise moment. F2 D2 is the clockwise moment. Here we are not taking some because two forces are considered. If suppose I am considering other forces also, let us say F3 and another one F4, then this F3 is at a distance D3, F4 is at a distance D4. Then we can say F1 and F3 will produce anti-clockwise moments. F2 and F4 will produce clockwise moments. If I sum up these anti-clockwise moments, and if I sum up these anti-clockwise moments, then the sum of the anti-clockwise moments will be equal to sum of clockwise moments. Principle of moments is that one. So we can say the sum of clockwise moments is equal to sum of anti-clockwise moments. That is achieved from this expression. And mechanical advantage is the ratio of F1 divided by F2. Before going to this, I can say F1 is the force generally considered as the load to be lifted. Load to be lifted. And F2 is the force which we apply to lift the force. We used to call it effort. We used to call it effort. The distance d1 from the load end is called a load end to the center is called load arm. And the distance d2 from the effort end to the center or to the fulcrum is called effort arm. Effort arm. So load into load arm is equal to effort into effort arm. What is F1? The load to be lifted. What is F2? The effort applied to lift the load. What is D1? Distance of the fulcrum from the load end. We used to call load arm. What is D2? Distance of the fulcrum from the effort end. We used to call effort arm. So the product of load into load arm will be equal to effort into effort arm. So F1 is load, which is the output force. Which is the output force. Means you are going to lift the load here. You are going to lift the load. So we used to call it output force. And effort is the input force. You are applying the force. You are applying the force to lift the load. So you are giving the input. So effort is the input. So mechanical advantage is equal to output force divided by input force. Output force is nothing but load. Input force is nothing but effort. Mechanical advantage is equal to load divided by effort. Output force divided by input force. So what do you understand from this? If I bring out a condition that mechanical advantage is greater than 1, then I can say F1 is greater than F2 or F2 is less than F1. Also, we can write D2 is greater than D1. D2 is greater than D1. If mechanical advantage is greater than 1, then F1. Because I told you mechanical advantage measures the force amplification. Means force must be multiplied. Force must be increased. So if I am applying 10 Newton of force, then mechanical advantage is a measure which will provide a measure that I can able to lift a 100 kg object. A 100 kg object, which means mechanical advantage here is 10. So generally mechanical advantage must be taken to be greater than 1. So F1 is greater than F2. What does this mean? The load is said to have a greater magnitude when compared to the effort. A small amount of effort applied will lift a greater magnitude of load. That's the meaning. A smaller amount of force applied. How will you use or how will you make a huge stone to move aside? Simple. Use a crowbar. You use a small stone as the fulcrum. You just place the crowbar over there. Means at the point of fulcrum you just make a support. One end of the crowbar is given at the bottom of the huge stone. The other end is there in your hand. If you apply a small amount of force, you can see the huge stone lifted up and is rotated or is made to roll around. So what exactly happens here? You are applying a small amount of force. Effort is very small. And then the load lifted is said to be very huge. Means large amount of force is given as the output. And fulcrum is this point. Fulcrum is the point where the support has been obtained. So we can say here when mechanical advantage is greater than 1, F1 is greater than F2, which means load is greater than the effort, which indicates that a smaller amount of force that is provided is used up to lift a huge load. That's the meaning. And F2 is less than F1. I told you the idea. D2 is greater than D1. What is this D2? What is this D2? D2 is said to be the effort arm. D1 is said to be the load arm. Load arm must be always shorter. Effort arm must be always larger. If this condition is maintained, then you can easily lift a load. And that happens on the fundamental or on the basis of principle of moments. So once again, I would like to recall. Mechanical advantage is the ratio of load to effort, or load arm means effort arm to load arm. Effort arm to load arm. Load to effort or effort arm to load arm. You have to go through the expressions very carefully. If you are clear with this one, Sum of the clockwise moments equals sum of anti-clockwise moments, from which you can easily bring out this expression. This ratio of F1 by F2, load to effort, is called mechanical advantage. Once again, I would like to say mechanical advantage is the measure of the force amplification achieved with the machine tool. And we can say effort is always smaller, load is always larger, which indicates that a smaller amount of effort applied will lift a heavy load. That's the meaning. So this is all about the principle of moments. So once again, I would like to recall the definition for couple: a pair of forces equal in magnitude, opposite in direction, which are separated by a perpendicular distance, whose lines of action do not coincide, causes the turning effect in the body, is called couple. And the principle of moments, what is principle of moments? We can say, by the definition of principle of moments, we can say the body will be said to be in a state of rotational equilibrium when the sum of moments of all the forces acting on the body must be equal to 0. In other words, I can say the sum of clockwise moments equals sum of anti-clockwise moments. That is also principle of moment. And what is mechanical advantage? Is the measure of force amplification achieved with the machine tool. Mechanical advantage is equal to the ratio of load divided by effort, F1 by F2 is equal to effort arm divided by load arm, D2 by D1. If mechanical advantage must be greater than 1, F1 is greater than F2 or F2 is less than F1, which means effort is always less than the load to be lifted. So a small amount of effort applied is used to lift up a huge load. This is the key idea. Also, if you recall the conditions for translational as well as rotational equilibrium, you can have a clear picture about this couple and principle of moments. So idea is very simple. Idea is very, very simple. You can just go through it. You can go through the video. You can check out what are the conditions for translational equilibrium. If you look at the condition for translational equilibrium, the net force must be equal to 0. I would like to write it over here. For translational equilibrium, net force must be equal to 0, or the sum of the forces acting must be equal to 0. Sum of the forces acting on the body must be equal to 0. The linear acceleration will be equal to 0. Velocity must be equal to 0 or constant. That linear momentum is equal to 0 or constant. If linear velocity and linear momentum are 0, then the body is said to be in static equilibrium. If the linear velocity and linear momentum are constants, then the body is said to be in dynamic equilibrium. Static equilibrium and dynamic equilibrium are the different parts of translational equilibrium, different conditions of translational equilibrium. So this is how you have to list out the ideas here. Then for rotational equilibrium, the net torque will be equal to 0, or the sum of the net torques I equals 1 to n, tau I vector is equal to 0. Sum of the net torques acting in the body must be equal to 0. Sum of the moments of forces must be equal to 0. F1 d1 minus of F2 d2 is equal to 0. Sum of the moments of forces must be equal to 0. And we can write sum of the moments of forces must be equal to 0. F1 d1 minus of F2 d2 is equal to 0. And we can say angular acceleration must be equal to 0. Then angular velocity must be equal to 0 or constant. Angular velocity must be equal to 0 or constant. Then angular momentum must be equal to 0 or constant. Angular momentum must be equal to 0 or constant. We won't speak about this condition. We usually speak about constants. So angular momentum is a constant. Instead of saying 0, angular momentum is a constant, angular velocity is a constant, angular acceleration is 0. Angular acceleration is 0. If these conditions exist, then the body is said to be in a state of rotational equilibrium. Whenever you are going to speak about the couple or principle of moments, kindly go through this one. The states of equilibrium are very, very important. There are so many states of equilibrium discussed. Just go through one by one so that you will have a clear picture about all these ideas. Thank you.